Welcome to this explainer. Today, we're going to do something pretty incredible. We are going to completely freeze time and trace the sub-microsecond relay race between hardware and software during a RISC-V synchronous exception. Now, RISC-V synchronous exceptions are literally one of the most important mechanisms that ensure architectural correctness and system reliability, and today we're breaking down exactly how they work. Here's our roadmap for the steep dive. We'll start with the exception challenge, look at how hardware takes control, see how software drives the recovery, move on to decoding the cause, returning via met, and finally, wrap up with the minimalist philosophy behind the whole process.
So let's jump right into part 1, the exception challenge, where the system is on the brink.
We kick off our micro journey at the exact fraction of a nanosecond an instruction actually fails. Whenever an instruction causes an illegal operation, maybe a misaligned memory access, a page fault, or an ecall, the processor immediately halts the normal instruction stream entirely and initiates trap handling. It's really critical to separate this from an asynchronous interrupt, like a timer or some external hardware signal. A synchronous exception is a direct, immediate consequence of the program's execution that fundamentally tests the processor's architectural integrity. To handle this sudden halt, the processor has to figure out exactly where to go next. Now, while interrupts can use a massive dispatch table in what's known as vectored mode, synchronous exceptions act a bit differently. They always immediately redirect the program counter to the base address in direct mode. This entirely eliminates the need for a large software dispatch table, forcing a rapid, highly predictable jump to a single entry point. That brings us to part 2, hardware takes control, the immediate reaction. This is the moment the processor steps in to save the day before your code even knows what hit it. In a sort of bullet time pacing, we see the hardware automatically taking over. It saves the address of the interrupted instruction directly into the mepc register, records the exact reason for the exception in mcause, updates the mstatus register to preserve your privilege in interrupt state, and seamlessly redirects the program counter to the trap handler address stored in mtvec. And simultaneously, the hardware elevates the processor to this absolute fortress of machine mode privilege. This rapid transition from user execution straight into machine mode ensures that exceptions are handled securely and predictably. User applications absolutely cannot interfere with the trap execution from down below. The handler now has complete, unrestricted authority over the processor. Which leads us to part 3. Software drives the recovery, effectively passing the baton. So the hardware has done all this heavy lifting instantly, and now it passes the baton over to the software handler. Once inside the trap handler, software officially takes control of the recovery process. This is exactly where reference implementations, like the ones from the OpenSBI open source project, step in to manage the fallout. But there's a fascinating design choice here. You might be wondering, why doesn't the RISC-V hardware just automatically save all 31 general-purpose registers right then and there? Wouldn't that just be safer and easier for the software? Well, unlike some other architectures out there, RISC-V does not automatically save general-purpose registers, and that's entirely intentional. It's all about keeping the hardware simple and efficient. Instead, the handler saves only the specific registers it actually needs onto the stack. By leaving this register management up to the trap handler prologue, the recovery process becomes incredibly fast. This software-driven approach provides a ton of flexibility while heavily minimizing hardware complexity and, crucially, minimizing interrupt latency. Moving on to part 4, decoding the cause and finding the solution. With the necessary context now safely preserved on the stack, the software handler basically reads the hardware's notes to determine exactly what went wrong. The software examines the mcause register to pinpoint the exact cause of the exception. By decoding this abstract register into a tangible lookup table like you see here, the handler can branch directly to the correct recovery or system service routine. For example, a value of 2 means it caught an illegal instruction, while a value of 8 means a user mode application intentionally made an environment call to request a service from the operating system. The software then performs the required recovery based on that specific code and restores the saved processor state. Now for part 5, returning via mepc, where the handshake is complete. The really crucial point here is how we seamlessly transition back to normal user execution after the exception has been successfully resolved. To complete the trap handling sequence, the processor executes the mret instruction. Mret atomically restores the previous privilege level and interrupt state from mstatus. It reloads the program counter from mepc, and it smoothly resumes execution of the interrupted program. This atomic, all-at-once execution prevents any weird intermediate states where the system could be vulnerable or accidentally crash.
Finally, Part 6, the minimalist philosophy and why this all matters.
This seamless transition from normal execution to privileged exception handling and then right back again is a true cornerstone of the RISC-V privileged architecture. It beautifully demonstrates its clean, modular, and efficient design philosophy. It's so fundamental that it's taught in advanced operating system courses, like MIT's 6.1810 Operating System Engineering. By balancing a minimalist, deterministic hardware reaction with highly customizable software recovery, the open standard architecture achieves unmatched adaptability. It's exactly why RISC-V exception handling scales so well, whether you're dealing with a tiny low-power IoT microcontroller or a massive high-performance data center processor. The fundamental handshake is always the same. Which leaves us with this final thought for today. Think about how this minimalist approach really empowers developers. It strips the bloat out of the hardware and puts control firmly in the hands of software engineers. If you were designing a custom processor today, how would this modular hardware-software handshake change your approach to building reliable systems? Consider how you might utilize these exact mechanics in your own architectural designs. Thanks for joining me on this explainer, and keep exploring.